So I had to separate the original video into two parts because it was too long to load up to YouTube. So this is part 2 of the alkali metals. Okay, so let's look at the actual chemistry, the chemical equations. Here I've used lithium as my example. So I've got lithium, add into water. So as I put it in the water, and I'm going to make lithium hydroxide plus hydrogen gas. And that was the gas we saw coming off the lithium at the beginning. And that is my formula, my symbol equation. I could also do a written equation there, lithium plus water, making lithium hydroxide and hydrogen. But what about if I changed the lithium for the sodium? Well, I'm hoping you'd understand, guys, because it's group 1 and they've all got 1 electron on the outer shell, they're going to react in exactly the same way with anything else. So sodium is still going to react with water. It's not going to make lithium hydroxide, it's going to make sodium hydroxide. I can change my equation, sodium plus water, making sodium hydroxide plus hydrogen. And again, my word equation, I'm just simply going to swap out the name of the metal. So instead of lithium plus water, I've got sodium plus water. And again, I could do that for potassium plus water, making potassium hydroxide plus hydrogen. There's my change my formula, and there's my word equation. Now, some of you, maybe L1, L2, are probably having a heart attack right now because that symbol equation is not balanced. There you go, guys, it's balanced now. Just didn't want to confuse things. Okay, so I just want to zoom in on these equations. I could have easily written the same equations again for rubidium or cesium or francium, but we don't need to. We know what they're going to make. But I just want you to notice that these 3 products here, hydroxide, you should know hydroxide OH is an alkali. And this is where the metals for group 1 get the name alkali metals, because when you react them with water or indeed oxygen, you make an alkali. So if I'd have put a universal indicator, that lovely colour changing liquid, in the water when I finished doing these experiments, it would be this lovely purple colour. They're all alkalis. So another thing you need to know about the alkali metals is that when you add water, or when you add them to water, you're going to make an alkali. Okay, so hopefully you understand that we get more reactive, or the metals get more reactive as they come down the group. But to take that to the next level, you need to understand why. Why is francium so much more reactive than lithium? So to explain that, I've got a diagram here of lithium. I know it's lithium because it's got 3 protons, 3 electrons, and I can look at lithium. There's my atomic number at the top there, 3. For the sake of the conversation, I'm going to just assume or think about the nucleus as being positive, and I'm just going to think about the outside electron because those are the only things we're worrying about. Now, when an atom reacts, and we're talking about reactivity, it's all to do with the outer electrons. Is it going to lose it? And is it going to gain them? And how quickly or easily does it do that? So the more easily this element can lose that electron, the faster it reacts. Okay, so what makes it easy or hard to lose an electron? Well, it's all to do with how close together these positive nucleus and the negative electrons are. So in this example, lithium's quite a small atom and they're close together. And therefore this force here, this attractive force, positive and negative opposites attract, is quite a strong electrostatic attraction. So electrostatic attraction is the positive negative attraction that we talk about. And because they're close together, it is a strong attraction. Now that means if I'm trying to lose that electron, or lithium is trying to lose that electron, it's trying to react, that's going to be pretty hard because the positive is pulling it back in again. And so it's harder to lose the outer electron. And because it's harder to lose the electron, it's going to be slower to react. Now it will lose it. We know that because lithium reacts, but it just takes that little bit longer. Now if we compare to the group as we go down, you can see here I've got lithium, sodium and then potassium, and as we go down the group those atoms are getting bigger. Okay, so that's another trend. As we go down the group, the atoms get bigger. Now I haven't done that going downwards because you can imagine I've not got a lot of space on my slide. As you go down the group, the atoms are getting bigger. That's important. Let's look at a bigger atom. So here's a bigger atom, maybe potassium or rubidium. And you can see again, I'm just looking at the positive nucleus and the negative outside electron. Now look how much further apart they are. These are much further apart, and therefore that electrostatic attraction that's pulling them together, that's holding them together, is much weaker. So it's a weak electrostatic attraction. That means when this atom, say it's potassium, tries to lose that electron, it's going to be much easier to lose the electron because the positive force pulling it back in again is much weaker, and therefore it's going to be faster to react. So can you imagine that the bigger these atoms get, the weaker this force is that's holding them together, and so the easier it is to lose that electron to the water or to the oxygen or to whatever it is it's bonding with, and therefore they get more reactive. So let's think about how you would write that in a great deal of detail. As you go down the group, what is happening? Well, the atoms are getting bigger. So what? Well, the distance between the positive nucleus and the negative outer electron increases. Okay, but why is that important? Well, that means there's a weaker electrostatic attraction. That means it's easier to lose an electron, and that means it becomes more reactive. Now you can see how in an exam question you can go from answering it very basically, the atoms get bigger, they get more reactive, but the more arrows you put in, the more detail you put in, the higher the level you work and the better marks you get. I don't think any one of you would suggest that you didn't understand each of those arrows or hadn't heard of those arrows, but it's so easy to forget to write them down. Okay, so this is a flashcard I gave to my Year 11s when we thought we were revising for exams, and this is basically everything you need to know about the alkali metals using the dual coding. So what did we say? Well, we said it's group 1. We said that they're metals. We said that they are reactive, and we can say they're more reactive as we go down. We can say when we add them to water, they make an alkali. We said they cut easily, they are low density, and they have low melting points. Now what this flashcard doesn't do is then say why they're more reactive, but if you had memorised this flashcard, those memories of the properties and how they're connected would give you a starting point. My Year 11s found this really, really helpful when we were revising. It's a bit disappointing we didn't actually get to do the exam. For me, maybe not for them.